Hi guys, I wanted to make a quick video to kind of go over the last two portions of question 4 on the activity. So just for a refresher, this is what they were, right? We had to calculate an exact percentile, and then we also had to calculate an estimated percentile. So the answers to these questions, right, we say we want to look at why we have this discrepancy between these two percentiles. And just graphing this out, right, you should have seen that the data are positively skewed, meaning we have this tail on the right side, right, of our data, meaning there's some outliers that are pulling the mean to the right, okay? So the reason we would use skewness and kurtosis is because it's an evaluation of distribution shape, right? And the main difference between the exact percentile versus the estimated percentile, oh no, I'm having zooming issues, is that the exact percentile is calculated regardless of distribution shape, whereas the estimated percentile, right, is going to be calculated on the basis that we have a normal distribution. So the disagreement between the distribution shape between these two questions is what is causing this shift in our percentile. Okay, so I have this description right here. If you guys wanted to read that a little bit more, or like pause the video and read that. But basically what I'm going to be doing is taking this graph of what our actual sample looks like. So I'm going to attempt to draw. I think this will work out. Okay, so I first want to again go over how we calculate an exact percentile. Okay, so, and I apologize in advance for shaky hands. I am not cool and don't have like a stand for my phone that'll hold it up. So when we calculate an exact percentile, again, we don't care about the shape of the distribution. So we already know from graphing this, right, that we've got positively skewed data, meaning that we're going to have a tail on the right side, right, and the mean of our distribution, let's say it exists there, right, is going to be drawn away from where this other central tendency would be, right? So again, remember when we have a perfectly normal, oh no, pen roll. We have a perfectly normal distribution. Our mean, mode, and median. English is so hard. I don't even know if I just said those words right. So the mean, the mode, and the median, okay, all three of our measures of central tendency are all going to line up at the peak of our distribution. When we have the presence of extreme scores, right, let's say the majority of our data maybe ends here, but we have one extreme score that exists out here, that ends up drawing our mean to or towards that extreme score, which we can see in this example, right? If this is our mean, and this is our median and mode, it gets drawn to the right. Okay, so in our example, our mean was actually equal to 949. This is in watts. Okay, our standard deviation was, and I'm rounding, 173. Okay, so when we look at our distribution, there's a couple of ways, again, that we can label this. One being that our mean we know is in the middle. Okay. This could also be considered as 0 standard deviations from the mean because it is the mean, okay? And then what we could do from here is kind of use these values to guesstimate where 801 would exist, right? So if this is +1, +2, +3 standard deviations, and then same thing in the other direction, right? We can basically calculate what values would exist at each of these standard deviations by adding or subtracting, right, 173 respective to how far away from the mean we are. So in this case, we add 173 to 949 if we're going to 1 standard deviation away. That should approximately give us 1123. We add 173 again, that should give us 1296. Add 173 again, that should give us 1470, roughly, okay? If we go in the opposite direction, we say I want to go minus 1 standard deviation, so I minus 173, right? That would be about 776. Minus 173 again to get 2 standard deviations away, that would be about 602. Minus 1 more time, and we're at about 429. Okay, so when we have this raw score of 801 that we're interested in, right, we could fairly say that 801 probably lies between -1 and 0 standard deviations, right? So in this case, let's say that it's probably closer to -1, right? Just because this is close to 800, or closer to 800 than this one is. So I'm going to draw this dotted line, right? That's going to represent where X, or our raw score, is 801. And then we know for our exact percentile, at least, we found this to be 21.32%. Okay. All right. So now, have this in mind. When we calculate, I'm gonna skip ahead for a second. When we calculate an estimated percentile, remember, estimated percentiles, we use z-scores. And then when we do exact percentiles, we use our distribution calculations, okay? So when we use z-scores, again, you can kind of just take our general layout where the center is the mean, right? Okay. So when we take these z-scores, or when we use z-scores to find percentiles, right, we're operating under the assumption that about 50% of the data lies over here, and 50% of the data lies over here. And you can confirm this by looking at your z-tables, right? So positive z-table is going to say from 0, that should be the 50th percentile, or 0.5, right, all the way out to whatever the last number is in the positive z-table, should be like 0.9999 or something close to 100%. Okay. On the flip side, our negative z-table, where we have all of our negative standard deviations, that should be from 50%, again at 0, and then all the way out to 0.000 whatever, right? So close to 0% out there. So I think that's kind of the most important difference between an estimated and an exact, is this is based off of that you have a perfectly normal 50% on this side and 50% on this side. That's why we estimate it, because we never know if our sample is actually perfectly normally distributed, right? So let's say that we had a skewness value and kurtosis value that were within our plus or minus 2, right? Which would mean we're accepting them as relatively normal, but where they're not perfectly normal, right? In this case, we have perfect normal distribution. So to summarize, right, 50% of our data should exist on this side. 50% should exist on the other side, right? In the case where we've got this skewed data, right, remember the mean is going to be drawn to the right just because of a single outlier, maybe a couple of outliers on this right side. So that's going to cause an uneven distribution of frequencies on the right side of the mean compared to on the left side of the mean. And I actually calculated this for the example we have here. But what ended up happening is approximating our percentages. About 57% of our data landed on this side of the mean, and about 43% of the data in the given sample landed on this side of the mean. Okay, so what's going to happen is that this distance between 801 and 949, not technically changing, right? Because our actual unit measurements are fixed, right? So the distance between 801 and 949 is always going to be the same. The fact of the matter is that we're recognizing a higher percentage of data on this side of the mean than we are on this side, right? And if a higher percentage of data exists on this side, that means that from 801, we would expect a higher percentile, right? Versus when we look at our estimated values, again, we were in between. I think the z-score was like negative 0.86 or something like that. So within, but still between -1 and 0, similar to how we would be up here, right? And x is still 801, but our percentile, we noticed, was 19.77%. And why is this? Is because, right, we're assuming 50% is on one side of the mean, 50% is on the other side of the mean, right? So if we take this 801, we would assume less data to be over here, right, or to the left of this particular value, then we would expect there to be over here, because there's an additional 7% accounted for in our population than compared to our normal distribution, right? So that's kind of the biggest reason why this percentage is so, or not drastically larger, but this is why this percentage is bigger than this one, okay? Because this influence of this outlier in this area drew the mean this direction, it's not going to distribute the frequencies of values that occur in the distribution evenly amongst the mean, right? So greater percentage over here means that if we chose 801, there's a greater likelihood, right, that we're going to have a higher percentage existing to the left of 801. Versus down here, we have equal distribution of frequencies, right, on both sides of the mean. So we have a likelihood of lower amounts of frequencies, or a lower number, lower percentile, lower probability that we would land to the left of 801 in a perfectly normal distribution, okay? Hopefully that helps make sense, right? But the biggest difference, again, between exact and estimated percentiles is that exact percentiles, when we're using our distribution equations, are not concerned about the shape of the distribution, right? These inequalities of how points are distributed amongst, right, or around the mean don't mean anything to the percentile that we calculate, okay? Versus in an estimated percentile, we have to assume we have normal distribution in order to use that z-table, okay? So hopefully, again, that helps make sense out of things and emphasizes what the big difference is of when you use this one versus when you use this one, okay?